Okay, good afternoon. This paper is entitled Directed Greybox Fuzzing, and it's joint work with Marcel Baume, Thuan Pham, MD Nguyen, and myself. And we are all from the National University of Singapore. So the motivation of this, I guess, since we are going through the fuzzing session, and previous to this also we had another fuzzing session. I guess the motivation I can go over rather quickly. So, of course, the motivation of fuzzing is in automated vulnerability detection. And usually there are three kinds of fuzzing, as is probably well known to this audience. Black box fuzzing, where there is absolutely no program analysis. White box fuzzing, which is primarily program analysis. And I'll need to talk a little bit about that, given the nature of this work. And gray box fuzzing, where there is no program analysis, but there is a coverage feedback. So there is no particular program analysis being done to cover more and more paths, but there is some coverage feedback being provided by the fuzzer due to some instrumentation. Okay, so very quickly, the black box fuzzing, particularly commercial fuzzers like these ones, like Peach, they take in not only seed inputs, but also an input model. So nothing is known about the program, but you would typically have an input model that is given to you, and then you get mutated inputs. You mutate based on this input model, and you might get valid, semi-valid, or invalid inputs, and accordingly you would proceed. So you have absolutely no view of the program, but you have some view of the input domain. Compared to that, in white box fuzzing, you have perfect view of the program. So really speaking, you would assume that you can do a control flow extraction, and you can traverse the different parts of the program. And not only that, you can symbolically represent the path conditions, which is the set of inputs which go through this path. So here, this is a trivial program with three paths, and the corresponding path conditions are given. And the way it proceeds is usually you would start with a random input, you would construct the path condition, and then next time you mutate this path condition, instead of mutating the inputs, you mutate the logical formula a little bit, just so that next time around you get another input going through another path, and so on. Okay. So of course this requires heavy wet machinery. In between is gray box fuzzing, which is most popular, namely the AFL tool, where you have mutated inputs, seed inputs, and mutated inputs. And typically, you would try to retain the inputs that increase coverage. And the way you get the information about whether the input is increasing coverage is by instrumentation. And based on that, you would put these to this queue of interesting seeds, and then this process will continue with the goal of covering more and more inputs. Uh, okay. So gray box fuzzing is really speaking frequently used. It is the state of the art. Most of the talks we have had today afternoon really focuses on gray box fuzzing. I did not notice any talks on white box fuzzing or black box fuzzing. They were all on gray box fuzzing. It's an extremely efficient coverage based input generation. The trick in the efficiency is that all of the analysis, any analysis that is needed, whatever you need, is done at the instrumentation time. In particular, for the coverage-based gray box fuzzing, usually the analysis that you need is really the coverage information. So accordingly, you would do that instrumentation. You start with a seed corpus, you choose a seed file, and you fuzz it. And of course, you add the new inputs that you get to the corpus only if the coverage is increased. The main difficulty is that it cannot be directed, but it cannot be directed to specific dangerous locations in the program, whereas white box fuzzing is very, very suitable for being directed to dangerous locations in the program. Okay, but directed fuzzing, on the other hand, it has many, many applications. So, for example, patch testing, if you introduce some patches in your program and you want to test them, you would want to reach the patch in the first place for the purpose of crash reproduction. Suppose you have a crash and the user has reported, say, for example, when you have a bug report and you click send error report, on the other side, they will not get exactly the input. They will need to reproduce the crash based on a stack trace. For the purpose of verifying static analysis reports, static analysis, of course, as we know, can generate voluminous reports for verifying them that whether indeed certain locations are dangerous. and also for information flow detection. So there are really many, many applications of reaching a particular control flow or a particular location in the program. And if we could use the Greybox fuzzer for this purpose, that would be very nice without losing the efficiency of Greybox fuzzing. So the notion of directed fuzzing is such that just the definition of the problem is such that it is very, very suitable for white box fuzzing. For the symbolic execution based approach, this is inherently suitable. Usually, what you do is you do some sort of program analysis. It can be taint analysis, it can be other kinds, to identify program paths which reach the particular program location in question, which is the dangerous location that you want to reach, and then you would do symbolic execution along those particular paths to derive the path conditions. It may not be a complete path enumeration. You can probably do some amount of path merging and so on. And then you would do constraint solving to find an input which satisfies these particular path conditions. So just the nature of the problem is such that the white box fuzzing lends itself very nicely to this problem. But of course, this requires heavyweight machinery. So, what we are studying in this paper is whether we can achieve directed fuzzing through a modification of existing gray box fuzzers, and in particular, the most popular gray box fuzzer, which is the American Fuzzy Lop or AFL. Okay. So to suit the AFL fuzzer or the gray box fuzzers like AFL, we have to view the directed fuzzing in a slightly different way. In white box fuzzing or symbolic execution, this is seen as a constraint satisfaction problem. So you generate constraints by going along selected paths, and of course, you have program analysis to select those paths. And once you generate the constraints, it becomes a constraint satisfaction problem. To suit it to the gray box fuzzing, which is inherently a search based approach, we view it as an optimization problem. And the main viewpoint that we take is we will retain the efficiency of AFL. Any analysis that we do has to be at the instrumentation time or compile time. At runtime, we will not have any particular analysis. Okay. So we have to view, to fit gray box fuzzing into directed fuzzing, we have to view it as an optimization problem. At instrumentation time, we will extract the call graph as well as the control flow graph. Note that we will extract only the intra-procedural control flow graph. We will never generate the inter-procedural control flow graph, which typically has a notorious complexity. And for each basic block, we will compute a distance to the target locations. This will only be an approximate distance. This will not be the exact distance, as I will show in a minute. And then we will instrument the program to aggregate these distance values. So next time around, during the runtime, when you run particular seeds, we will just compute the distance to the location in question very, very efficiently, so that that can guide us to generate other inputs where we can reduce this distance and hopefully make the distance zero so that we can reach the dangerous location. So just so that it's clear, the viewpoint itself has changed. Now we see it as an optimization problem, that is optimizing this distance, as opposed to a constraint satisfaction problem where you are trying to find the input as one solution to a constraint. Okay, so at runtime, for each input, we will essentially collect this coverage and distance information. And then based on the distance, we will decide how long it is to be fuzzed. In particular, if the input is closer to the targets, then it is fuzzed on for longer, because hopefully we are hot in our pursuit to the dangerous location. And if it is further away, then we try to move away from that location. So this is really the intuition. So now I will show how the distance is computed at compile time. And it would not be an exact computation of the distance, because we don't want to generate the interprocedural control flow graph. So we will start with the call graph. On the call graph, we have to first find the target functions. In this case, we just have one target function maybe. And then for each function, we will compute the length of the shortest path to the target. If there are multiple targets, we take the harmonic mean, but that's a detail. So for one target, we will just compute the length of the shortest path. So this is quite straightforward. Now, when we come to the intra-procedural control flow graph, and this is where the approximation comes in. So I'll just bear with me for a minute to explain this. So in the intra-procedural control flow graph, we have to instrument each basic block with the distance. So we'll identify the target basic blocks, of course, and I assign a distance 0. Suppose in this function, say the one for this particular function b, so this is the control flow graph, there is none. And then we will identify other basic blocks which call functions. So we will not generate the interprocedural control flow graph. We will identify basic blocks that call functions. And for each of these, with the function level target distance that we obtain, we will multiply it with some constant. So this constant you can tune. If this is just an approximation because we don't want to compute the exact distance. And then, of course, for each basic block, we will then compute the, say, in this case, the harmonic mean, the length of the shortest path to any function calling basic block plus this constant times the function level target distance. Okay. So we can already see what is happening. We are trying to compute as exactly as possible while only constructing the intra-procedural control flow graphs. So we are trying to compute the distance as exactly as possible, but we don't want to construct the inter-procedural control flow graph. So once we compute this distance, then we will essentially annotate each basic block with this particular distance. This is all done at compile time. Note that this is all being done at compile time. And then later on at runtime, when you have the seeds and you want to find the distance of the seed, you will just you will just go through the path that the seed traverses, and every time it goes through a basic block, you just add up the pre-computed distance for that basic block that was computed earlier on in compile time. So we only had to change to achieve this way of directed fuzzing. Actually, we only had to change the AFL instrumentation in a very small way. I would say the change in the instrumentation was not difficult. We had to just add these two entries. One is the aggregated basic block level distance, which means that, say, suppose I'm going through an input which traverses this path. I come to this node, I just add 8.7. Now my distance is 8.7. Now I add 30, so it is 38.7 and so on. So this is all I need to maintain. And then another entry, which is the total number of executed basic blocks. So once you maintain these two information, then given a seed, given the path that it traces, the path that is traced by the seed, you can compute the distance as a single number of this seed to the dangerous location that you want to reach. And this is the distance that you will use to further tune your search so that you can optimize the overall distance and hopefully reach a distance of 0 so that you can reach the dangerous location in question. Okay? So this is really what is being done at runtime, very efficient, and the AFL instrumentation is just being changed with these two entries, and in compile time we are computing the distances for each basic block while still constructing only the intra-procedural control flow graphs, not the inter-procedural. Okay. So in this particular case, this is the seed distance. Okay. So now that we know how to compute the seed distances, we can just see how to minimize it. So as I mentioned earlier, we will view directed fuzzing as an optimization problem. And of course, I'll give a brief background of the coverage-based Greybox fuzzing, which is known to this audience. So there are a number of mutation operators, which we are not touching. And given the mutation operators, the mutated inputs are generated. You try to retain the inputs that increase coverage, and you put them into the queue of interesting seeds, and the process continues. And of course, in coverage-based Greybox fuzzing, there's this process of assigning an energy to the seeds. And in our case, we will try to give high energy to the seeds which are closer to the dangerous location in question. Okay. So the energy that is given to a seed in coverage-based Greybox fuzzing is really the number of inputs that you will generate from this particular seed by mutating it. So this energy schedule is the only one we are changing. In past work, we have done this work on AFL fast, which assigns more energy to seeds that exercise low frequency paths. This was mentioned in one of the other papers also I saw. So in this work, we are not using AFL fast because AFL fast has already been integrated into the main line of AFL, the idea of AFL fast. So we are taking that version of AFL and we are introducing this directedness just so that the implementation is clear. Okay, so just to make it completely clear, this is in fact the schematic algorithm for Greybox fuzzing, and the only place we are changing is this assign energy. So how do we change it? We assign more energy to seeds that are closer to the given targets, and the problem is if we just use stochastic gradient descent, then we will always assign more energy to closer seeds, and this would typically end up in a local minima. In search-based techniques, this is a well-known problem, and we of course don't want to end up in a local minima. So we use this simulated annealing approach. So here is a schematic to explain the issue very clearly. So suppose this is the global minima you want to reach at the bottom of this valley, but of course, if you are here, then you have to cross this small hill first before you can fall down. So you really have to sometimes increase the distance before you can go down and reach the global minima. So how do we tackle this seemingly contradictory concerns? This is being done through this cooling schedule, which is well known in simulated annealing. So the cooling schedule really captures the importance of the distance. If we are always very greedy, we always say that we want to reach the shortest distance very quickly, then we will get stuck in a local minima. So we are not greedy. Initially, we assign equal energy to all seeds, but gradually, according to the cooling schedule, the temperature reduces, and then the importance of the distance becomes more and more. So this is the general idea, and integrating the simulating annealing as a power schedule, the exact formula of exactly how the power schedule works, that is of course there in the paper, but here is a schematic to explain it. So initially, say at time equal to 0, you can assume that all seeds get the same energy. At time equal to, say, I don't know, 10 minutes, just as some random number, you can see that already seeds that are a bit closer, they get more energy, and seeds that are at a more distance, they get a bit less energy, and this becomes sharper and sharper as the time progresses. So really, from exploration, you get into exploitation. Initially, you are in the stage of exploration, and from exploration, you will gradually get into exploitation. Here is another way of explaining the same concept, where we have plotted it against time. So if the distance for seeds which are very close to the dangerous location in question, you can see that they get more and more energy as time passes by, but seeds that are further off, their energy will wither off. So we have implemented this idea of the distance-based directed gray box fuzzing on top of AFL. In particular, the version of AFL which already integrates the explore schedule of AFL fast. And we have looked into the use of it in a number of applications, including patch testing, continuous fuzzing, and crash reproduction. So I will briefly mention some results on this. So in patch testing, we are trying to reach change statements, and we are comparing with the state of the art in patch testing as of now, which is actually based on symbolic execution on the CLE symbolic execution tool. It's called Catch. So one would expect, because symbolic execution is very suited for reaching directed locations, one would expect that symbolic execution would be more suitable in terms of reaching locations than this kind of an input generation approach. But what we found out by using exactly on the same set of programs used by the symbolic execution based approach is that the results are a little bit different. So here we are showing the results on these bin utils and diff utils, and the number of changed basic blocks are shown, the number of uncovered. These are the ones which are uncovered after running through the test suite that is already coming with these programs. And these are the number of basic blocks among the uncovered that are covered by catch. And these are the numbers that are covered by AFL Go. So you can see that the results are better. So here we are not comparing the efficiency. Efficiency wise, everybody knows that gray box fuzzing is more efficient. We are comparing the effectiveness, and it also turns out that gray box fuzzing in this case is more effective than symbolic execution when directed in a suitable fashion. There are still a lot of cases which are uncovered, and this is oftentimes due to register indirect jumps because the control flow graph itself is incomplete. We also notice that there is a significant number of cases where either the symbolic execution approach is able to handle it or the gray box fuzzing approach is able to handle it. So this also leads us to believe that there is substantial potential in combining these for the purpose of patch testing. We also looked into the number of vulnerabilities that you can find by reaching these patches for the purpose of patch testing, whether you can find new vulnerabilities. So previously in catch, these were the number of reports that were there. So 4 of those we were able to regenerate, but we also found number of new reports. Do note that the catch experiments were done a few years back in 2013. So since then, more vulnerabilities have been found and fixed. So we are not including them here. So these are ones that exist as of today. These are completely new vulnerabilities that exist as of today, and that was found using this directed gray box fuzzing approach. Okay, we also tried out this approach on the crash reproduction problem. So the crash reproduction problem is, say, you are working with an application like PDF reader or something, and then probably it crashes on you and it asks you whether you want to send an error report, and then you say that yes, send. Then on the other side, the developer has to reproduce the problem, and in this case, we assume that the input that is given is only the stack trace. And again, we are comparing our result based on the directed gray box fuzzing with a symbolic execution based approach in CLE, which is a bug redux. Okay. And in fact, these are the results. So in almost all the cases except one, and I'll just explain in a minute why that one we cannot handle, AFLGO was able to reproduce the crashes just based on the stack trace. So given the stack trace, it will treat all of those as potential locations to reach and compute a aggregate distance to all of those locations. Only for one we could not reproduce, and that's for a technical reason because we are only generating one file as input, whereas this particular program takes 2 files as input. So that's more of an engineering reason rather than anything else. And the symbolic execution based approach, it seems, again, needs more hints, which is again a little bit surprising because you would expect symbolic execution to be able to traverse paths more effectively. And in this case, it turns out that it needs more hints. It needs a more detailed method signature. Okay. So in summary, we have presented this work on directed gray box fuzzing, which seems to outperform the symbolic execution-based directed fuzzers in terms of effectiveness. The efficiency comparison, I guess I didn't get into, but efficiency-wise, it is expected to be better. It has also been integrated as an OSS fuzz fork. There are a number of CVEs that have been reported, as well as number of bugs that have been found in the security critical libraries, and fair amount of details on that is available in the paper. Everything in terms of the artifacts, everything on this is already available, and this link is also present in the paper. So everything can be downloaded from here. And that brings me to the end of my presentation. So as a motivation, we tried to say that directed fuzzing has been classically been a constraint satisfaction problem, and we tried to show how this can be instead seen as an optimization problem. And then we achieved this as an optimization problem by modifying the power schedule of AFL in a dual way, where there is the temperature schedule and there is also this power schedule based on the distance. And then we showed some applications in terms of the crash reproduction as well as patch testing. So that brings me to an end. Thank you very much, and I'm happy to take any questions.
Hi, Yufeng from UT Austin. So great talk and great work. So I like the idea of reduce the problem of this direct fuzzing, gray box fuzzing to the standard optimization problem. So I was wondering whether in your case when you build a weight for each base block, right? Is it possible that since you turned it into an optimization problem, can you just directly reduce that to a standard max set problem? So basically, each solution of the max set will guarantee that the paths that you enumerate will always be the shortest. And then you just block the model from the max set solver one by one. So is that going to work compared to the temperature?
Yeah, I think that's a fair point. So we did not want to put any constraint solving here. In fact, the current generation maxset solvers, and I have worked with them on other problems, not in this particular problem. The current generation maxset solvers are, in fact, not very efficient. And in particular, you would not be able to deal with maxsat for this problem. If you wanted to use maxsat, you would need to use a max SMT solver,
Right.
and a max SMT solver is not very efficient to deal with in the first place. But certainly the problem, if you want to look at it as an optimization problem, you could encode the optimization problem in a max SMT solver. That's a fair point.
So basically,
But
sorry.
but there is particularly no specific need to do that, as was shown. Even with an SMT solver, you can just see this as a constraint satisfaction problem, because your goal is to, in the end, just reach that location, not necessarily reach it through the shortest path.
I see.
You see, so the only reason we are turning it into this shortest thing, because we want to deal with this efficient search based technique, but we want to give it some guidance. And we cannot give the constraints as guidance, because that would be too inefficient. And that is why we have turned it into this optimization problem, and we have the distance calculation.
Okay.
Yeah.
Thank you.
Eric Dad CISPA, great work. I'm having a question about so basically, if you consider spending a couple of effort in generating a call graph to increase the precision of your distance metric, would you think that this would improve your results substantially? So did you try that out?
Yeah, I think it would improve the results. In particular, I think the results would improve if the control flow graph was more complete, more than the call graph. I think the control flow graph we would benefit more, because we still have, as you saw in the results on patch testing, there are still a number of basic blocks in the changes which are not being reached, and most of those, majority of those, more than 50% of those are due to register indirect jumps, which are not being handled properly in the control flow graph, in the intra procedural control flow graph construction. But that was not something we are studying. That's like an orthogonal issue, because this issue is always there. How do you generate the control flow graph in the most complete way? So given any standard control flow graph construction, I'm trying to see how best I can reach a particular location. Of course, if my control flow graph is more complete, this technique would be more effective. That goes without saying. Yeah.
Thank you.
Let's thank the speaker one more time.